some poles. After 2 years, the poles will have shifted like that, which is the Poisson velocity gradient for a very highly viscous flow. And it is exactly the same way in which, even though this is entirely different scale, the fluid in a small capillary move, which would be highly viscous, it would also have that velocity profile, that it would be dragged by the boundary, so it wouldn't move at the boundary, and its velocity would be maximal here in the middle. And it's exactly the same what happens for the ice field in the iceberg. Not iceberg, but you know, the
glacier.
Yeah, glacier, that's what I mean. So Reynolds number actually enables us to compare all these different situations and tell that all of these can be modeled by one equation. Glaciers, small animals, or honey. And that's interesting about Reynolds number, that it just shows you the qualitative understanding of things. So, as we limit ourselves to low Reynolds number, and I can erase the terms that are not important, I'm left with so-called Stokes equation. So, I don't need to copy anything, I just copy that. Over rho plus mu del squared u. I can take it the other way.
Is that P or rho on the top?
P.
P. I don't know which idiot decided that they would add rho and P look so similar. It's silly. It's like U and V, isn't it?
Sorry, I don't know.
It's tragedy waiting to happen.
It's usually up to lecturers' handwriting. Where mu is this viscosity that I defined at the very beginning. This was viscosity, this was kinematic viscosity, and this was density.
Is there a sort of intuitive way of thinking about kinematic viscosity?
Yeah. I think.
How
You mean what is the intuitive way of thinking about
what is it? Viscosity, you can think of, you know, how quickly a sort of, I don't know, hemisphere of fluid is going to flatten itself to, you know, on a table or whatever. But kinematic viscosity, does it have what's the best way of sort of intuitively thinking about that? Or is there no point? You could just let the maths do the same.
Well, the density itself, it's hard to think of a quantity which would be independent of the density. Because this is the intuitive way what we were talking, that the viscosity is surely connected to the density of the fluid, because you can measure how does it flatten out, how does the jet look like. So the kinematic viscosity would have to do only with the property of the fluid itself, but not with the density. And I'm not entirely sure if I can explain it in an intuitive way.
Don't worry about it.
I do understand the viscosity in such an intuitive way, but nevertheless this was the Stokes equation. And that's why flows in the low Reynolds number that I'm going to be considering are called in a variety of ways. Stokes flow, creeping flow, potential flow, or simply low Reynolds number flow, which is the most descriptive of all. So now I will show a video showing, I've talked about that, we'll talk about that in the future, organisms and swimming and mechanical models I will all show during the presentation. This is the guy about whom I was talking about, E.M. Herschel. He published the paper that I based my presentation on. And I just wanted to show you the video of low Reynolds number fluid.
Microscopic effect.
Where is it? Oh, here you are.
With a little fuzziness due to the down on it.
Here we go. It's a classic experiment.
The space between them is filled with glycerine. Into this space I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction.
This shows very nicely one of the crucial properties of fluids described by the Stokes fluid. That's why I show it.
Turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
Wow. That's amazing.
And it goes back.
That's
To see
incredible.
what happens, we have a second apparatus that is filled with syrup. It has a wider gap.
But what happens is just that
Okay.
all the what? Oh yes, he comes. But that what happens is that all the layers move separately.
During the forward motion, the boundary of the fluid follows a path determined at each instant by the motion of the wall. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops.
So because they have very high
During the
inertia.
reverse motion, the boundary of the fluid position.
Oh, the very low
The
inertia.
motion
So
of
they
the
stop
body is also
almost
reversible.
instantaneously.
Here is one with a gap to mark its orientation. This is set initially in the 12 o'clock position.
This shows that
The motion carries the
Motion is
body
reversible.
around and also makes it rotate.
and time independent.
On reversing, the rigid body returns to its original position and orientation.
I'm sorry.
A flexible body, like this bit of yarn, is inserted. The reversal of stress will alter the shape of the body, so that it will not return to its original position.
Have someone. I was just looking. I was just. In the meantime, I have derived Navier-Stokes equations, shown the high viscosity limit, and derived what is Reynolds number. And now I'm just about to start talking about biological motility in the regime of low Reynolds number, based on this paper. So we arrived at how do animals move in low Reynolds number in fluids with low Reynolds number, in fluids which have these wild properties that anything that happens in them is entirely reversible, and it has such a high viscosity that you would need to develop entirely new ways of swimming. So first we would have to think, what does it mean to swim? I put on into my presentation mostly all the images from Purcell's paper, and he actually published it like that. So not pictures have to be made in paint or any nice application for drawing. It can be just handwritten.
Presumably the reason this is so unfamiliar, these shapes returning to exactly their original form, is just that all the fluids we're familiar with have high Reynolds numbers.
Yeah, like water.
So it's just totally, we never really come into contact with.
Exactly. This is what I was just talking about. That we have in general very low force, very small Reynolds number, and Earth's mantle also has got a very small Reynolds number, and that the definition of Reynolds number is exactly as I have defined it. Length times velocity times density divided by the viscosity. Now it's interesting to think how far does anything move when it stops propelling itself. In a water, you can think of a boat that turns off its engine. It's gonna continue to move for quite a long way. So what happens if a Suberlak stops propelling itself? How far does it move? You can guess that it's not gonna move quite a long way, but it can be calculated. So I have a bacteria, like here, with these dimensions of about A would be of order of micrometer. It moves with a velocity of about 30 microns per second. My inertia would be about 10 to the minus 2 centimeters squared per second. Sorry, Percival used CGS. So I didn't translate all of the units into the SI system. And the drag that this ball experiences in the highly viscous fluid is going to be the Stokes drag, which is 6 pi eta A nu. Then I can use the second law, Newton's second law. So MA equals the drag. Rearrange. Solving, I get an exponential. It will be log, but I mean it's going to be log, and then I have to get rid of log, so it's going to be exponential. Where the time scale tau would be m over 6 pi nu a. It's one of the back of the envelope calculations which I did just before the presentation, so you can trust me, it's right. And then we can integrate that to get the distance, how far did it go. So I just need to consider the initial velocity and the time scale that I derived, which gives me, when I plug numbers, the distance of about 700ths of an angstrom with tau of about 0.2 microseconds from this formula when I plug in rho